Hello, welcome to my channel. My name is Loanch, and in this video we're going to look at projection of a vector. Okay, great. Okay, so this video just be a quick one. We just want to get the idea behind projection of vectors, and then we'll look at how to get that, and then we'll just close. All right. Okay, so if you find this video helpful, please don't forget to subscribe to my channel. Okay, great. Now, given two vectors, let's say we have two vectors, A and B. All right. Good. Then the projection of vector, let me put it out here. Now the projection of vector A, okay, in the direction of vector B, so this is how to write it. That is the projection of vector A in the direction of vector B, okay, should be understood as, now is understood as the portion of vector A pointing, all right, in the direction of vector B. So the portion of vector A pointing in the direction of vector B. So maybe let's just get some illustration. So let's say this is vector A, then this is vector B, all right? Okay, that's nice. So let me just indicate that this is vector B, then this is vector A. Okay, maybe let me clean this off a little bit because I may need this space. Okay, so let me write the vector B here. Okay, now the projection of vector A onto vector B is the portion of vector A pointing in the direction. Now this is how to think about it. It's like the shadow, all right, of vector A on vector B. Use another different ink to denote that. So it's like the shadow of vector A on vector B, such that it is perpendicular to the direction of vector B. Good. So that is how we want to think about it. So this portion from here to here is the projection of vector A in the direction of vector B. So as you can think about it, the portion that is like a shadow, right? Okay, great. Now, how can we make sense of this? Well, noting that this right here is a rectangle, triangle, right? We could easily use, okay, and I forgot to point out that these vectors, that the directions of vector A and vector B, is the directions are inclined at an angle of theta. Okay, so in our previous video we dealt with scalar product or dot product of vectors. We could easily say that, okay, we don't even need to use it, but in the previous video to motivate us a lot, right? Now look at this. Looking at this, we could see that that cosine of this angle, it's simply the length of this side, right, which is the length of the projection of vector A in the direction of vector B. Okay, that's the length of that side divided by the length of the longest side, which will be the length of vector A. Good. So to get this projection, we could easily just cross multiply, right? So that will give us the length of that projection of vector A in the direction of vector B to be the length of vector A, okay, times cosine theta, which is as the angle between them. Now this length of vector is what we call scalar projection. The scalar projection of a vector onto another vector, it's simply that. So it's simply the length. All right, so if you want to look at what is the length of vector A pointing in the direction of vector B, you just look at that shadow, kind of a shadow of vector A on B. That's if you have a light flashing directly above this vector, okay, the reflection on the direction of vector B will be from here to here, which is perpendicular. That is if the light is directly above, right, which is perpendicular to that. That's why we have 90 degrees over here. Okay, great. But in our previous video, so we dealt with dot product of vectors. We could get from there that cosine theta is simply, let me put down the length of vector A. Now this cosine theta is simply the dot product of those two vectors, vector A and vector B, okay, divided by the product of their length, right? That is the product of their sizes, that is B right here. Of course, these are just numbers, so maybe we could cancel this and that because they're the same. So that will leave us with A dot B divided by the length of vector B. Good. So this is the, like I said, I call this the scalar projection of vector A onto vector B. Scalar because this just gives us the length. So the scalar projection is the length. Now, I want you to make sense of all of this. In one of the previous videos where we applied unit vectors, okay, that is a concept from unit vectors in solving some examples, we're able to see that to get a vector pointing in the direction of another vector, you have to multiply it by a unit vector pointing in that direction. So if you're looking at the direction of vector B, this right here gives us the unit vector pointing in that direction, right? Then this is just the vector A itself. So it makes a little bit of a sense together if you combine that with our definition right here. So like I said, this right here is the scalar projection. Now, since I've mentioned scalar projection, so what about if we want to look at a vector projection? So for a vector projection, we would like to give it a little bit of a direction. And since the direction should be the direction of vector B, I would simply just multiply a unit vector pointing in the direction of vector B, and the result will give us a vector projection of vector A onto vector B. Okay, so I call this scalar projection. All right, scalar projection. Now, to get a direction, that means we're going to have that the projection of vector A onto vector B, in this case, is no longer a scalar, it's no longer a length, it's now going to be a vector itself, will be this same product that we have here divided by length of vector B. Okay, then we multiply that by a unit vector pointing in the direction of vector B, that is this multiplied by this. Okay, so you could easily combine these two together. So let me combine them. And then by combining them, I don't have space right there. Let me just put it down. I don't have enough space. So by combining them, we'll have this to be, we could write it as A dot B, all right? Then divided by, of course, this and this are the same, so you just say the square of the length, which is same thing as saying the dot product of vector B with itself from the previous video when we dealt with dot product of two vectors. So this right here is the vector projection of vector A onto vector B. Okay, so this is the result. This is also correct, it's just that I've rewritten it, right? Okay, great. Now, I would like us to make something out of this, something that would be very useful, or that is very useful in the next video in the series. Okay, so let's make some observations. Let me put it out here. All right, great. Now, in the definition, in our previous videos, we defined the dot product of two vectors, that if you're given vector A and vector B, then the dot product is length of vector A. Then we had this, right, where A and B here represent the length of vectors A and B respectively. Good. Now, using this result from the scalar projection, observe how it looks. Or maybe we can start from here. Okay, by this observation, we could see that we could also rewrite this, the dot product of vectors A and B, as the length of vector A times the projection, the length of vector A times the projection of vector A in the direction of vector B. Okay, how would that span out? So let's see. This is the length of vector A. We multiply it by, now what is the scalar projection? Not just any kind of projection. Okay, I should say a scalar projection, please. So what is the scalar projection of vector A in the direction of vector B? This is it. So I'll just substitute that. Scalar projection of vector A in the direction of vector B will give us vector A times vector B divided by the length, this should be the scalar projection of vector B in the direction of vector A. Sorry, let me just switch things. Okay, so it should be the length of vector A times the scalar projection of vector B in the direction of vector A. Yeah, that's how it should be. So what is the scalar projection of vector B in the direction of vector A? We just have to switch the order. Excuse me. Okay. Hopefully that's not too bad. Okay, now we just have to switch the order, because this one was the scalar projection of vector A in the direction of vector B. Okay, that is this. So we just have to switch the order, which means we'll have the scalar projection of vector B in the direction of vector A will just be divided by the length of vector A. Okay, so you see that these two lengths will cancel each other out, leaving us with vector A dot B. So this was just a way of saying this is the same thing as that, which means that this right here is true. So I just wanted to show you that, all right? You don't need to get to this point. Okay, so what does this mean? That to compute the dot product of two vectors, we could simply just say the length of the first vector times the scalar projection of the second vector in the direction of that first vector. It will still give us the dot product of those two vectors, and that's simply from what we observe here. Of course, you notice that this cosine of theta is the same thing as that, of course. So you could just make sense out of that. Just look at it again and again. Okay, so in the next coming videos, we've proved some theorems, especially this theorem, that the dot product, that the distributivity property holds with scalar products of two or more vectors. So that's what we'll be doing. That's what we've done in the next video. So please just check that out. Okay, thanks for watching. I hope you enjoyed the video. Please don't forget to subscribe to my channel, share the video with your friends, and we'll continue from our next video.